Alright, welcome to the lunchtime video. So I had a rare evening video yesterday where we did some extra work on the this topic. So we're going to be doing hopefully just one more video on the topic. There was just some good information in the Mpls Day 1 book that I didn't want to just kind of leave on the table. So we're working on bandwidth configuration for Mpls Rsvp LSPs. So let's get right back to where we were. Okay, so this is traffic engineering, Rsvp bandwidth constraints. So I left a note for myself, and then I created the title for the next video. Alright, and my glasses are pretty dirty. I don't have any. I don't have a microfiber cloth though. Oh, shoot. I thought I had one somewhere. Oh man. Nope. So I think I have one. I'm gonna pause and come back. Okay, so it's a little better, not great, but let's continue. So I have the place I left off right here. So let's do a control and a find, and there's a really loud noise outside, like a beeping noise. It kind of sounds like a phone call or something, like a busy signal. Maybe somebody's like ringing my apartment. I didn't know that was possible though. Like I've never, like the gate is like, doesn't, like I've never been rang before. Yeah, I'm not sure what's going on out there, but I don't hear that noise anymore, so let's continue. This is auto bandwidth in action, an example. The next section shows an example of auto bandwidth in action. Consider the following configuration on Levagulin. Okay, so yeah, and we're not using that naming, so let's see which one has. Okay, so this will look familiar. It's the same configuration I have on PE1. Oops, let's maybe get a better. Okay, that's a little bit easier to read. Yep, and I've got the extra trace options, but yep, I've got the same configuration they do. Jesus, that's a loud noise. Oh, it's just a FedEx truck. Normally it's not so loud. Okay, so initially 100 megabits per second of traffic is sent over the Lagavulin to Oban LSP. The bandwidth shown for the LSP is slightly lower than this due to the averaging over time. Okay, so the next part is show Mpls LSP name. There we go. So max average bandwidth until, let's see if we've got that. We do, but for ours it's 0. And bandwidth, so we've got 64. So it looks like there's some issues on ours, but let's just keep going. The amount of traffic is then increased to 150 megabits per second. Notice the max average bandwidth util value increasing above the value of the LSP's reserved bandwidth. A manual request for automatic bandwidth allocation adjustment is issued. This has the same effect as the adjust interval timer expiring. Okay, well I don't see where they had that, but let's see if I can remember. Oh, so they do list it right here. Let's enter that command in. Yeah, I would have gone with clear, so I'm glad they listed it because I don't know if I would have found that right away. Okay, so now let's see if there's some differences. Oops. Oh, so we're still at 0 here. Not sure what's going on with that, but it's definitely not matching what we've got here. It looks like our log here is quite a bit different here. Here we can see automatic auto bandwidth adjustment succeeded, but there is no such message in mine. I don't see that one did not succeed. Let's check the other one. Okay, so we're missing this automatic bandwidth adjustment succeeded command. And we do have it added to the label switch path. So yeah, I don't understand what's going on. Okay, so yep, and sure enough, we don't have any of these messages either. Note that the allocated bandwidth for the LSP changed from 90.4 megabits per second to 110.7 megabits per second. The LSP adjusted its bandwidth because the max average bandwidth value was greater than 20% of the previous average when the manual request was triggered. Keep in mind that the manual adjust auto bandwidth request evokes the same behavior as the adjust interval timer expiring. The LSP initiated a make before break call to signal the new path before moving the traffic. Understand that these values represent the maximum average traffic, not the maximum traffic over the measurement periods. Since this data comes from a lab environment and uses the adjust auto bandwidth manual adjustment trigger, the time periods for traffic measurement are artificially shorter than those for a production network. Warning: automatic bandwidth allocation adjustment does not create bandwidth, but can only act as a tool to help optimize existing bandwidth and assist in understanding when it is time to augment the network. It is certainly not a substitute for proper network planning, but rather a tool to assist in efficient utilization of existing resources. Okay, planning for sudden LSP bandwidth increases. So I kind of wish I had gotten this to work. I think what the issue is that it's only going to make changes based on these values, and right now I've just got no I just have no traffic going through at all, so of course it's not going to make adjustments. Oh, we got some framing errors. That's interesting. But yeah, there's definitely not. I mean, we've got a 1 gig link. There's just not enough traffic to make those adjustments. Yes, I'm trying to generate some traffic, but I just don't know if I'll be able to generate enough just using the regular ping. I'd have to do like a file transfer or something, like multiple file transfers, which I could probably do somehow, but let's just keep going. I kind of, 5 videos is quite a lot of videos. There's other topics, so let's keep going. Planning for sudden LSP bandwidth increases. Typically, an LSP's adjust interval is configured for longer periods of time, sometimes hours or days. In this example, it's configured for 7,200 seconds or 2 hours. During that time, there may be a large increase in traffic on the LSP, potentially causing congestion and/or packet loss. This is typically not an acceptable condition that should go on for hours. The adjust threshold overflow limit feature is designed to deal with this type of situation. The Lagavulin to Oban LSP shows this additional configuration below. Alright, so let's add that. So one of the things I could do is, whoops. Okay, well, I'm going to stop that. Okay, one of the things I could do is put a Linux server here, and then make sure they can ping each other, and then transfer a file and see how the utilization on the links increases, and then set up values to watch this in action and set up the trace options, look at the log messages, all that sort of thing. I could do that, but as is, I think I'm going to be pretty much fine for now. Let's just keep going. Let's add the extra configuration to PE1. Perfect. This LSP's adjusted threshold overflow limit is set for 2 Mpls statistics intervals when the adjust threshold overflow limit is configured. After each Mpls statistics interval, 600 seconds in our example, the following conditions are checked for the LSP. Did the average bandwidth utilization for the LSP during the interval exceed the current maximum average bandwidth utilization? Has the change in the maximum average bandwidth utilization exceeded the configured adjust threshold? These conditions can often be difficult to understand. Let's consider an example. An LSP's maximum average bandwidth shows up in the show Mpls LSP name detail output once auto bandwidth is configured. See output below. In the example below, the current max average bandwidth util value is 90.4 megabits per second. At the end of every Mpls statistics interval, the LSP's reserved bandwidth, 25.7 megabits per second in the example below, is compared to the max average bandwidth util value for that period. If the max average bandwidth util is greater than the LSP bandwidth, 0.1 is true. If the change in max average bandwidth util exceeds the adjust threshold, 20% in our example, then 0.2 is also true. So I believe the points are the questions here. Did the average bandwidth utilization for the LSP during the interval exceed the current maximum average bandwidth utilization? That is 0.1, so 0.1 is true. If the max average bandwidth util is greater than the LSP bandwidth, and that is determined at the end of every Mpls statistics interval by comparing the LSP's reserved bandwidth to the maximum average bandwidth for that period. Okay, so 0.2 is true, and 0.2 is, has the change in the maximum average bandwidth utilization exceeded the configured adjust threshold? That is true if the change in max average bandwidth util exceeds the adjust threshold. In our example, it's 20%. Okay, so yep, all the settings are gonna match. It's just the results of the configuration are gonna be different because I don't have the same lab they do. So yep, you can see here they've got. This is very true. My average bandwidth is definitely gonna be 0. There's just nothing going over there. If I can leave, why don't I go on PE2? And just leave a running ping forever, and we'll see if that average goes up. Now, it's the average over a cycle, and I don't remember what the cycle was set to, but if the cycle is set to a long cycle, such as like 10 minutes, that might be just too long. We can always bump it down, but for now, let's just let's do a show configuration protocols Mpls. Oops. Oh, right, because there's no, okay, so let's do a show run int, show configuration int. Yep, so 255.0.1, so ping 10.255.0.1, and then let's send the biggest packet we can, just because I think that will use more bandwidth. Okay, so now hopefully we'll eventually see this average utilization increase. Okay, and you can see it's going to make the adjustment soon. So after that timer has expired, we will see that. Now, unfortunately, this is a very long timer. Let's try changing that interval so that we can actually see the differences. And you know what? I might actually pin up to Linux servers. It's not even 12:30 yet, so I think I might have time to do that. But let's do a configure private, edit protocols in Mpls, edit, and then show pipe display set relative. Okay, and now let's go to the label switch path. Perfect. So yeah, so this adjust video interval, this is going to be way too long for our purposes in the lab. So let's set it to every 30 seconds. That might be too short, but let's see what we got here. Oh, so yep, that's 30 seconds is going to be too short. Our shortest amount of time is 300 seconds. So let's set it to that. And I think 300 seconds is like 5 minutes. So even that's a pretty long time, but that'll be short enough. Okay, and hopefully we'll see this yeah, we'll see this change now that I've got some of the links more saturated. Okay, but until then, we're gonna move on. So if conditions 1 and 2 above are true, then the sample is configured to be one bandwidth overflow sample. The adjust threshold overflow limit statement allows you to configure a limit on the number of consecutive overflow samples. When the limit is reached, the LSP's current adjust interval timer is expired and the LSP adjusts its bandwidth. Once the adjustment occurs, the adjust interval timer then starts again from 0. It is important to understand the difference between the adjust interval and the adjust threshold overflow limit. The adjust interval is best suited to handle more gradual increases or decreases in bandwidth over a longer period of time. The adjust threshold overflow limit, on the other hand, is best suited to deal with more dramatic increases in bandwidth requirements over a relatively shorter period of time. Note, at the time of this writing, the adjust threshold overflow limits can only increase the LSP's bandwidth allocation. The ability to decrease LSP bandwidth allocation based on sudden decreases in bandwidth is not available. Downward LSP resizing, if necessary, is done at the end of each adjust interval period. And I don't see really why you would need to do that, because if you're just not utilizing everything you have available, I don't see the reason to just it's like, you know, if I tell somebody they can spend $30 a week and they only spend $5 a week, I don't understand why I would need to tell them that they can now only spend $10 a week. Now, if I told somebody they could spend $30 a week and they spent $35 a week, then I could understand why you would want to raise that and say, hey, you could spend $40 a week. But to me, it's not surprising that there's no ability to decrease LSP bandwidth allocation based on sudden decreases in bandwidth. Okay, so let's see here. We've got, so this hopefully expired. Oh, nope, it's still going down. So let's just do a pipe refresh 3 on that, and let's do a pipe refresh 5. So every 5 seconds we're going to see this again, and then we'll just continue reading. Most dash least. So most fill, least fill, random fill. When multiple equal cost paths exist to the same destination, it is possible to configure an explicit CSPF, constrain shortest path first, the algorithm used to determine the LSP's path, tiebreaker based on the ratio of a path's available bandwidth on a link to total reservable bandwidth on the link. A method for tie breaking is necessary because an LSP's RRO, the sequenced list of routers that the LSP must transit, can only have one path. The tie breaking options are most fill, least fill, and random. Potential LSP paths with differing amounts of available and reservable bandwidth are compared by a ratio of each link's available bandwidth divided by its reservable bandwidth. The available/reservable ratio for a link is known as the available bandwidth ratio. Available bandwidth ratio equals available bandwidth divided by reservable bandwidth. The output from show Rsvp interface displays an interface's available and reservable bandwidth. Okay, so let's wait the 30 seconds and see if that average utility goes up now that I've got some traffic going through. Now there's no guarantee that it's going to go through the same links that the LSP is formed over. In fact, I believe it most assuredly will not, because it will just go through here, and the LSP that we're checking right now goes through here. So I don't think there'll be changes, but we will see that right now. Aha, yep, and there were no changes. So that's because the traffic did not use the same links. Well, you know what I can do? I can just do a ping instead of to the other side. I'm pretty sure it's going to utilize. So it's going to utilize one of these links. So it's definitely going to go over this link. So if I utilize some traffic on this link, maybe it'll show up that way. So I'm going to start a new ping, and it's going to be directly across the wire. And we'll see if that changes. So let's do a show int descriptions. So now we've got the one on the top is PE2, so it's going to be here. Okay, so across the wire, I believe is going to be .8. Let's check. And we can do a show ARP to check. Okay, so it's going to be .3. Okay, and let's do the maximum size again. Oops. Oh, I see. So it's a little bit, there's a frame header added on, so it's a little bit bigger. So yeah, now maybe this is going to go up, but let's do that command first. Okay, so we're looking at our Rsvp interfaces. Aha! So there's something interesting going on here. In the output above for the GE002 on Dalwhinnie GE002.0 is showing a reservation of 150 megabits per second, 850 megabits of available bandwidth, and 1000 megabits of Rsvp reservable bandwidth, shown as static bandwidth in the output. So interface GE-002.0 has an available bandwidth ratio of 850 divided by 1000, or 0.85. It's possible to cap the amount of bandwidth that the Rsvp protocol can reserve on an interface by specifying a bandwidth value in the protocol's Rsvp stanza. Here is shown Dalwhinnie GE002 capped at 500 megabits per second for Rsvp bandwidth reservation. So we have similar configuration on ours. It's going to be in protocols Rsvp, and if I do a show pipe display set, pipe no more. Oops, so actually we don't have similar configuration here. Before we did have link protection. So let's add that just for fun. Before we do that, let's rerun that command. Let's add it to the candidate configuration. So this will be available bandwidth for the interface. I believe we did this before, but let's just do it again. And then this is going to be link protection. So this is protect traffic with a label stack LSP. Okay, so this is going to be our candidate configuration, but before we make it the active configuration, let's recheck this command and see if we've got nope. So but it looks like the it hasn't adjusted yet. So I guess I'm willing to wait for the extra 49 seconds. Let's just keep on reading until then. Notice how the static bandwidth changed from 1000 megabits per second. Default value for static bandwidth is the interface's physical bandwidth to 500 megabits per second. This modification changes port 2's available bandwidth ratio to 350 divided by 500, or 0.7. In this example, table 1.2 lists each CSPF tiebreaker method and the general network behavior associated with each. So for most fill, and before I continue with that, we got 9 seconds, so let's see if we have some utilization now that there is a ping going over one of the links that will be used in the LSP. Nope, so we got nothing, and it is in the units of bits per second, so even just a small ping, I would expect, I mean, this is a lot of bits, so yep, it's just not showing up for some reason. Let's try, let's before we read this, let's try a ping. Oops, so let's do a no. And then let's do a commit and quit. And then let's try a ping. Well, I don't know, let's just keep going. So this is most fill, and then general behavior for the option most fill. Prefer the LSP path with the link that has the highest utilization, which means the least amount of available bandwidth. So the lowest available bandwidth ratio. This generally results in links with some traffic becoming close to full before less utilized links are consumed. Okay, I don't understand why you'd want that. Note the lowest available bandwidth ratio of a given path is the single lowest available bandwidth ratio belonging to any one of the links in the path. This is an important point to understand. The determination of the path with the most fill is determined by a single link in the path with the lowest bandwidth ratio. So let me open up Paint here so I can kind of explain my understanding of this. So let's say we've got a topology that kind of looks like what we got in GNS right now, where we've got 3 different paths where we can send our traffic, and then of course we have a LSP going between these two here. So if I can get like a crayon or something, some special here, yeah. So the spray paint, that's our LSP. So of course it can pick any one of these links. If we've got the most fill option enabled, whichever of these links has the most amount of bandwidth associated with it is the one that will be used. Is the one that will be used until it's maxed out. So I guess that kind of makes sense if you want your backup links to only be used if they absolutely have to be used. But I would kind of think that you'd want to spread out your traffic more. But I guess that could make sense, because if you want, and like if your packets are arriving out of order and stuff like that, so most fill kind of makes sense. So least fill is, of course, prefer the LSP path with the least utilized links, larger amount of available bandwidth, so a higher available bandwidth ratio. This generally results in more even distribution of traffic across the network. Randomly select one of the equal cost paths. As long as one of the equal cost paths has enough reservable bandwidth, it is a candidate for the additional traffic. This is the default setting. Configure the CSPF equal cost tiebreaker at the edit protocols Mpls LSP name hierarchy level. For example, Lavagulin's Lavagulin to Oban and Lavagulin to Oban prime LSPs are configured for most fill. The router uses the path containing the link with the lowest available bandwidth ratio until that interface is filled up. Okay, so they're going with most fill. Let's do that same thing. Oh, and they're doing it for the second one as well. Okay, so tip, when using most fill, least fill random for the CSPF tiebreaker, it is generally a best practice to use only one method across all the LSPs in the network. The CSPF tiebreaker method for an LSP can be confirmed by checking the detailed output of the show Mpls LSP name detail operational command. Okay, so we can see we've got load balancing set up for most fill. Tip, configuring many options and features common to many or all of the LSPs may become tedious. Junos groups, a type of template, can simplify configuration by applying common configurations to selected LSPs. The example below applies auto bandwidth attributes to all LSPs. Oh, okay. So they're making a group called LSP attributes, and that makes it a bit more tidy, because when you go here, you can simply. Oh, okay. So you don't even have to apply it there. It's just inherited. Let's actually try that. Just to. I'm not going to be using that on the test, I think, but it is definitely, in many cases, a good idea to use apply groups in the production network. One thing I don't like though is just using an apply group for everything just because it's an option. Like there's reasons to use it, there's reasons not to use it, but there are enough reasons to use it to make it worth the time learning how to do it. Okay, so it looks like they've got a typo in theirs. These are not going to be under protocols, they're going to be under protocols Mpls. I think. Oh, actually they'll probably be under, the editing probably accidentally took them out of there. Okay, so now we've got an apply group. So let's commit that. Okay, so now they've got it kind of strange, but I think you would go edit protocols Mpls and then set apply groups LSP attributes. Yep, and then now in order to see what has been applied, you go show protocols Mpls, but you're not going to see what comes from the apply group unless you do pipe display inheritance. Yep, so we've got these extra things coming from the apply group. Okay, but I'm not gonna commit the apply group unless I already did. I already did, but okay. Let's do a run or a show Mpls LSP name. Oh, so here they have an extra LSP that I haven't set up. And this is the last page, so let's just read this and then we'll be done with this. When looking at the configuration for the LSP, the configurations from the applied group do not show up unless the pipe display inheritance is added to the CLI show command. The show Mpls LSP output confirms that the Lagavulin to Dalwhinnie LSP has the attributes configured in the apply group. More, an in-depth discussion on Junos groups is beyond the scope of this book. More information on this Junos feature can be found in the Day 1 book, Configuring Junos Basics. A free download is available. Okay. Summary: this chapter covered concepts and different possible characteristics of an MPLS core network in a brief fashion. It is not meant to be an all-inclusive reference for each available concept in the core, but having said that, you should now have a basic understanding of the differences between LDP and RSVP, what an LSP is, the choices and trade-offs for each method of RSVP-LSP failover, and the many different methods of traffic engineering and LSP bandwidth management, as well as a few base configurations for each concept. Now that you have an understanding of the MPLS concepts in the network core, let's move on to Chapter 2 and its concepts for MPLS services, the next logical building block. Let's not do that because that's not necessarily directly on the test. Let's mark this topic as done. Okay, and now instead of moving on to that concept, we're going to be moving on to the next topic on the exam, and that is going to be TED. So as part of this video, I might, because I've got some extra time here, I might even just, I'm going to make my notes file. There we go, and then I'll add my tags, all that. Oops. Here it is. So okay, so now this is just going to be TED. Okay, and it's going to be the first video. So let's, yeah, let's just right here, right now, do the help apropos to load this up, get it ready for next time. Oh, so we've got a lot of false positives here for generated. So let's include the spaces so that we can get. Okay, so I don't see anything for just TED on its own. How about a dash? Nope, nothing for that. Oh, so here's the expected. So anything that's past tense and ends with a T is going to, any word like that is going to be a false positive. Looks like we do have a hit here for TED accuracy, so let's include that. Okay, so let's try this again, and we'll do TED, and then we'll do a second match for Mpls. Okay, so that's all we got. Let's see if there's anything in this book for the TED. Okay, so this looks pretty good. So well, never mind. That was just a brief thing. Let's find a search through. Let's find a topic by using a Google search. Okay, and then instead of the abbreviation, let's try typing it out a bit more. Here we go. Yep, we've got a full, got plenty of good resources if we don't abbreviate that. Okay, we've also got some hits for OSPF and, yep, so for OSPF. Got a full lab for that, but I might just take the extra 5 minutes. I got a meeting at 1 anyways, so yeah, I'll just look through these. Okay, here's a whole so traffic engineering. Okay, this looks like a decent one. Is this good? I guess I'm not sure. No, this one doesn't look any good. This one looks okay. Okay, so thanks for watching. We finished the Rsvp bandwidth constraint configuration. I think I did that justice. I feel really good about that. So in the next video, I'll be looking more in depth at the traffic engineering database. So thanks for watching, and I'll see you in the next one.